Howdy class. So today we're going to be talking about chapter 3, sections 3, 4, and 5. And this is just a reminder for any of you that need it. Again, I'm just going to show this for the first couple weeks, I guess, but office hours, my email, and then Nick and Austin's emails, okay? And then just a reminder, labs are going to start this week. So, sorry, labs are going to start this week, the week of the 31st. So make sure you check your schedule and you know what time you need to be in lab. You should be getting and by in lab, I mean on Zoom this week for everybody. You should be getting an email sometime today from your TA with the Zoom link. It's only the first week that's going to be on Zoom. So you don't, so if you are in person, don't worry, that didn't change. You don't need to purchase the electronic lab manual or the course site until then. You don't have anything that's due before then. So just check that email, get that REEF, or sorry, not REEF, get that Zoom link and attend the Zoom meeting, and then you'll get all the information during the Zoom meeting that you need. So make sure you, if you are new to the class, make sure you go on eCampus and read our syllabus and check out these documents for getting started. You need to change your Alex to my class. I think I've probably gotten everybody taken care of now, but just in case. And then you need to join our REEF course. REEF points are going to start counting this week, for real, this time. You don't need to worry about this stuff. This is old news. So sorry, I put that on here. All right, so chapter 3, section 3, the properties of atoms cannot be properly described using classical physics. Classical physics is designed for the macroscopic world. And when I say classical physics, I mean things like Newton's laws of motion, where every motion or every action has an equal and opposite reaction, things like that. Mass times acceleration equals force. That still sort of holds on the atomic scale, but we'll see how things do differ. One phenomenon that led to the birth of quantum theory was called black body radiation. So black body radiation is what happens when you heat up a solid. So if you heat up a piece of iron, or if you heat up old school light bulb, the incandescent light bulb, like I showed you in that demonstration video last time, in my last lecture video, that was a light bulb. When you heat it up, it gives off radiation, and you see it as a continuous spectrum. Now, not all things give off a continuous spectrum. Like we saw in that video as well, we saw that there were atomic line spectra, which we're going to talk about more today. So, in order to try and understand why the radiation that's given off by these heated solids comes out in certain wavelengths, like when you heat a piece of iron, it's going to be red hot. So to try to explain that, a guy named Max Planck proposed the concept of quantum physics, in which energy is only emitted or absorbed in discrete amounts. So when I say discrete amounts, I mean very specific amounts. It can't be emitted or absorbed in just any amount you can think of. There are certain amounts that it must be emitted or absorbed in. And these amounts are called quanta. So the smallest amount of energy that can be emitted or absorbed is a quantum of energy. And multiple quantums are called quanta. Let me erase that real quick. Okay, all right, so, and to describe these quanta of energy, we have this equation. So energy of one photon, or of one quantum, so any quantum, when we're talking about light, we're talking about photons, and I'll show you why in a second. But the energy of one quantum in joules is equal to Planck's constant, which is 6.63 times 10 to the negative 34 joules seconds, times the frequency in hertz, or 1 per second. So you can see here that if you have joule seconds times 1 over seconds, these seconds are going to cancel out, and you'll end up with joules. So you should also note that this Planck's constant is very, 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 very small. So whenever we're talking about Planck's constant, we're talking about things on the quantum scale, very, very tiny, almost unimaginably tiny things. All right, so this quantum physics was able to describe a phenomenon that was known at the time in the early 1900s called the photoelectric effect. So particles of light called photons, Albert Einstein was the guy who decided to call these particles of light photons. We previously talked about light as a wave, but now we're talking about light as a particle. So this is that wave-particle duality that you might have heard of before. So particles of light called photons carry energy based on the frequency of light used. So based on this equation, where E equals H nu, where nu is our frequency. So the energy is based on the frequency of the light that is used. You can use this energy to generate a current when you shine light on metal above a threshold frequency. So generating a current just means that you are ejecting electrons. The electrons are going to this anode, and they're being measured on this current meter. So here's a close-up of what that looks like. You shine the light on the metal. This is the metal, these close together atoms. If you remember, solids are densely packed and they have a nice ordered structure. So that's what this is. That's a metal. And when you shine that light on the metal, the electrons come off. And then, like I said, they are attracted to the positive anode and they go to the current meter. So there is a threshold frequency. The energy of a photon matters. So when you use light below a certain frequency, it doesn't matter how intense the light is. The intensity is more related to the amplitude of the wave, not to its frequency. So no matter how intensely you shine the light, if it's below a certain frequency, it won't eject any electrons. It won't generate a current. So the energy of each photon matters. So you can have a whole bunch of photons. That's what it means essentially when you have more intense light. You're producing more light particles, you're producing more photons. But if those photons don't each have the right amount of energy, nothing will happen. So there's a threshold frequency and consequently a threshold energy that these photons need to have to eject the electrons from the metal. And that's going to be different for every type of metal. So different metals have different threshold frequencies, but you guys don't need to worry too much about that. But just remember that energy is only related to the wavelength, whereas the number of photons is related, I'm going to use this proportional symbol, to the intensity of the light. The energy doesn't change, just the number of photons with that energy. Okay? So this is just breaking that down. Photons have a particular quantum of energy related to their wavelength. So we talked about it being related to frequency, but now I'm going to just substitute c over lambda for frequency to get E equals hc over lambda, because a lot of the time you're going to know things about the wavelength of the light and not the frequency. Sometimes you'll get the frequency and then you just need to use this version, but if you get the wavelength, you want to use this one. All right, so the energy of one photon in joules is equal to Planck's constant, which is this really, really, really tiny number, times the speed of light divided by wavelength in meters. So the meters, very important, has to cancel out with the meters in the speed of light. So we need to make sure all of our units cancel out so that we finally end up with the joules in energy. Okay, so we're going to use this equation to solve a practice question. What is the energy of a blue photon? Hint, blue is 450 nanometers. So our equation is energy is equal to hc over lambda, because c over lambda is equal to nu. So we want to plug in all of our constants now. So we've got 6.626 times 10. Is that what I had on the previous slide? No, I used 6.3, sorry. No, we're just going to use 6.626. That's one more significant figure than we need, I guess. So to the negative 34th joules seconds, and that's going to be multiplied by 3.00 times 10 to the 8th meters, per second. PowerPoint doesn't always cooperate very well. Divided by our wavelength. So 450 nanometers, and nano is 10 to the negative 9th meters. So if we convert it to meters, we're going to get 450 bloop, 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 times 10 to the negative 9th meters. Okay, so our joules, not the joules. The joules are the ones that don't cancel out, sorry. All right, so our seconds cancel out, our meters cancel out, and we're going to end up with joules. So let's plug that into our calculator. And when we plug that into our calculator, we're going to get 4.4 times 10 to the negative 19th joules. So note that there were 2 sig figs in our wavelength for the photon. So there are 2 sig figs in our answer. So the energy of a blue photon is 4.4 times 10 to the negative 19th joules. Okay, so let's talk more about this atomic line spectra thing, or this emission spectra thing. So sunlight is just like a light bulb. It's a continuous light source. So this is what they knew back in the 1900s. They knew that sunlight produced white light when you, and then when you shone it through a prism, you got this continuous spectrum, like what we saw with the light bulb in my demo video in the last set of lecture videos. But unlike this white light, unlike sunlight and unlike light bulbs, excited atoms have discrete line spectra. So those atomic line spectra that I showed you in that video. That means that the energy of an atom is quantized. So we'll see what that means in a little bit here. But this is a breakdown of what I showed in that video. So here's our discharge tube. That was the bright light that was before you used the prism to break it down. And they're shooting a high voltage or powering a high voltage through that discharge tube, which is exciting the atoms of the gas that's in the discharge tube. And then when you use a prism to separate the various components of that light spectrum, we see this. So this is the line spectrum for hydrogen. It has 4 discrete lines, 4 individual specific lines. So 4 specific wavelengths of light are produced when we excite the atoms of hydrogen. And they didn't really know how to explain this back then, but they were able to find a mathematical relationship between the wavelengths. So to explain why there were different wavelengths. And that is called the Rydberg equation, which we're going to see a more sophisticated version in a few slides. But the Rydberg equation just describes those individual wavelengths of light that we see. And it describes them as, or describes them using integers. So n1 and 2 are both integers. So that means they're 1, 2, 3, 4, like they're whole numbers. And this constant, the Rydberg constant, was able to relate each line in the atomic line spectra, so each wavelength of light in the atomic line spectra, to these discrete states, these integer values. So this is a fun little figure that shows you different line spectra of the different atoms. So here is hydrogen. It has this bright purple line, a blue line that's kind of hard to see on this figure, a brighter blue line, and then this red line over here, which is what we saw here. So red, light blue, darker blue, or indigo, and then purple. So we've also got helium here, neon, which has a lot of very bright lines, which is why they use it in neon signs to, have nice, bright, colored displays. We got all the other, there's a bunch of other atoms on here. You can take a look at them. This figure is also in your textbook. So enjoy. All right, so because scientists knew the basic structure of the atom, they needed to reconcile that with the physics of the atom. So one thing that they did was they stated that electrons are orbiting the nucleus, like planets around the sun. So say this is the nucleus of the atom, and this is an orbit, and another orbit. So the electrons are, traveling around the nucleus in these orbits, and and that was a little difficult to explain because these electrons are charged particles, and if they are accelerating in a circular fashion based on classical physics, the electrons would eventually spiral into the nucleus and cancel out with a proton in the nucleus. But this doesn't happen. So to explain why that didn't happen, a guy named Niels Bohr, B-O-H-R, came up with the idea that electrons can only orbit at certain distances away from the nucleus. So certain radii of these orbits. So these orbits can't be any size. They are discrete, specific radii orbits. And because they're at these certain distances away from the nucleus, the electrons possess specific energies there. So they need to have a certain energy to keep them away from the proton because of electrostatic interactions. So electrons and protons attract each other. So the electrons need to possess a specific amount of energy to keep it in orbit. And those energies, since they're specific discrete numbers, we call them quantized energies. So this quantized thing that we keep talking about just means that there are specific numbers. It's not just any place that the electron can be, but specific distances with specific energies. So think of it like a set of stairs. This is how your book describes it. You can't be, if you're going up or down a staircase, you can't be here. You've got to be on the step. Or you can't be here. You've got to be on the step. So those are discrete locations, just like the electron has discrete energies. And Niels Bohr came up with this equation to describe these energies. So the energy of an electron in a certain orbit, so the orbit is going to be based on this integer. Again, n is an integer, so n can be 1, 2, 3, so on and so forth. So when n is an integer, the energy is a specific energy related to that integer. And we describe n equals 1 as something called the ground state. So that is the lowest energy the electron can have. Because note, this is a negative number. So the energy of the electron cannot be any smaller than that number. Because when you plug in 1 here, that's just equal to 1. So this is the smallest energy the electron can have, because n has to be an integer and it can't be 0. So 1 is the smallest it can get. So that energy is the smallest it can get, 2.179 times 10 to the negative 18th in joules. Negative, sorry. And then the reason that we describe it as a negative energy is because we think of a free electron as an electron that is infinitely far away from the nucleus. So it feels no attraction to the nucleus. So this electron is so far away, it doesn't feel the nucleus at all, which means it has 0 attractive energy to the nucleus. So if we have 0 joules of energy, that means that n has to be infinitely large. So we describe the energy of the electron as attractive energy to the proton. So that's why this is a negative number. So the closer the electron gets to the proton, the higher the magnitude of the negative attraction energy. Okay, so this is really complicated, but the actual equations and formulas you need to use, not so bad. So just, you might have to watch this a few times for it to make more sense, or read the textbook, have it explained to you in a different way. But the formulas aren't too bad. But it's helpful to understand how they came up with these formulas before you use them. So anyway, a free electron is infinitely far away from the nucleus. So that's why we use the infinity sign as our value of n. So it's infinitely far away from the nucleus, and it has 0 joules of energy, no attraction whatsoever to the proton.